Imagine you are standing on an open field on a quiet morning. The sun is rising. It is warm on your face. You have seen this 1,000 times. It feels safe. It feels permanent. But what if I told you that the thing keeping you alive is also the thing most likely to end everything you have ever known? That the light warming your skin right now is the byproduct of a continuous thermonuclear explosion so violent that it converts over 600 million tons of hydrogen into helium every single second. That it has already destroyed planets, that it has already tried to destroy ours, and that it will eventually succeed. The sun is not your friend. It is a controlled catastrophe. And the only reason you are alive is because the balance has not tipped yet. But it will, and it is already started. Let's begin with what the sun actually is, because most people have never really thought about it. They see a bright disk in the sky, a source of warmth, a yellow circle in a child's drawing. But the sun is not gentle, and it is not small. It is a sphere of plasma, 864,000 miles across. You could fit 1.3 million Earths inside it. It accounts for 99.86% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, every grain of dust drifting between Mars and Jupiter, all of it combined makes up less than 0.2%. The sun is not part of the solar system. The sun is the solar system. Everything else is debris caught in its gravitational pull. At its core, temperatures reach 15 million degrees Celsius. The pressure is 265 billion times greater than the atmospheric pressure on Earth's surface. Under those conditions, hydrogen atoms are stripped of their electrons and slammed together with such force that they fuse into helium, releasing energy in the process. This is nuclear fusion, the same reaction that powers a hydrogen bomb, except the sun does it continuously, and it has been doing it for 4.5 billion years. Every second, roughly 4 million tons of matter are converted directly into energy and radiated outward as light, heat, and radiation. That energy takes about 8 minutes to reach Earth, and when it arrives, it sustains every living thing on the planet. Without it, the Earth would be a frozen rock drifting through the void at minus 270 degrees Celsius within days. But here's what most people don't realize. The sun is not stable. It never has been. It is slowly, measurably getting hotter. When the sun first ignited 4.5 billion years ago, it was about 30% dimmer than it is today. Since then, its luminosity has been increasing at a rate of roughly 1% every 110 million years. That might sound negligible, but it is not. It means the sun you are looking at today is not the same sun the dinosaurs lived under. It is not the same sun that shone on the first single-celled organisms in Earth's oceans. It is brighter, hotter, and more powerful, and it is still getting worse. Now let's talk about what happens on the sun's surface, because this is where things start to get genuinely frightening. The surface, called the photosphere, sits at around 5,500 degrees Celsius, hot enough to vaporize any known material. But this is actually the coolest part of the sun that we can see. Just above it lies the chromosphere, and above that, the corona, the sun's outermost atmosphere. And here is where one of the greatest unsolved mysteries in all of astrophysics lies. The corona is hotter than the surface, not slightly hotter. The corona reaches temperatures of 1 to 3 million degrees Celsius, sometimes spiking as high as 10 million degrees Celsius during solar flares. That is roughly 200 times hotter than the surface directly below it. Imagine walking away from a campfire and finding that the air 10 feet away is hundreds of times hotter than the flames. It makes no intuitive sense. Heat is supposed to decrease as you move away from its source, not skyrocket. Scientists have been trying to explain this for over 80 years. They call it the coronal heating problem, and despite decades of research and multiple space missions dedicated to solving it, nobody has a definitive answer. The leading theories involve magnetic reconnection events called nanoflares, which are essentially billions of tiny explosions occurring constantly across the sun's surface, and a type of magnetic wave called alpha waves that may carry energy upward from the interior. But the truth is, we still do not fully understand the mechanism that superheats the sun's own atmosphere. We are orbiting a star whose basic behavior we cannot explain. And from that superheated corona comes something that affects every planet in the solar system: the solar wind. It is not wind in any way you would recognize. It is a continuous stream of charged particles, mainly electrons and protons, blasting outward from the sun at speeds between 400 and 800 kilometers per second. At its fastest, the solar wind can reach over 3 million kilometers per hour. It floods the entire solar system, extending far beyond the orbit of Pluto, creating a vast bubble called the heliosphere. Every planet, including Earth, exists inside this bubble, constantly bathed in a river of solar radiation. Earth's magnetic field deflects most of it. Most of the time, that is enough. But sometimes it is not. And this is where the sun goes from being a distant threat to an immediate one. On September 1st, 1859, a British astronomer named Richard Carrington was sketching sunspots through his telescope when he saw something that had never been recorded before. A sudden blinding flash of white light erupted from the surface of the sun. It lasted about 5 minutes. Carrington did not know it yet, but he had just witnessed the most powerful solar event in recorded history. What followed was a coronal mass ejection, a massive eruption of magnetized plasma that launched billions of tons of charged particles directly toward Earth. It crossed the 150 million kilometers to Earth in just 17.5 hours, a speed that stunned scientists then and still impresses them now. When it hit Earth's magnetosphere, the effects were immediate and global. Auroras were seen as far south as the Caribbean, Central America, and Colombia. In parts of the northern hemisphere, the sky was so bright that people woke up and began their morning routines at 1 a.m, convinced the sun had risen. Gold miners in the Rocky Mountains started making breakfast in the middle of the night. Birds began singing, fooled by the glow into thinking it was dawn. But the beauty masked something far more dangerous. Telegraph systems across North America and Europe failed simultaneously. Operators reported sparks shooting from their machines. Telegraph paper caught fire. In some cases, operators disconnected their batteries entirely and found that the machines continued to function, powered by the electrical currents the storm had induced in the telegraph wires themselves. The Earth's own infrastructure had been hijacked by the sun. That was 1859. The world ran on telegraphs and gas lamps. Now imagine that same event happening today. In 2013, a joint study by Lloyd's of London and Atmospheric and Environmental Research estimated that a Carrington-level event in the modern world could cost the United States alone between $600 billion and $2.6 trillion. Power grids would fail across entire continents. Transformers, the massive machines that regulate electrical flow across national grids, would burn out. These are custom-built machines that take 12 to 18 months to manufacture and cannot be easily replaced. Satellites would be disabled. GPS would go dark. Communications networks, banking systems, water treatment plants, hospitals, everything connected to the electrical grid would be vulnerable. And here's the part that should make you uncomfortable. Research into the agricultural impacts of such an event suggests that the disruption to industrial production, including fertilizer and pesticide supply chains, could reduce global crop yields by 38 to 48%, with some regions like Central Europe facing losses as high as 75%. Global crop yields could be devastated. This is not a hypothetical scenario from deep time. On July 23, 2012, the sun unleashed a coronal mass ejection of Carrington-class intensity. It tore through Earth's orbital path at over 2,000 kilometers per second. But Earth was not there. We had moved past that point in our orbit roughly 9 days earlier. 9 days. That is the margin by which modern civilization avoided what some researchers have called a potential multi-trillion-dollar catastrophe. We did not dodge it because we were prepared. We dodged it because of orbital mechanics. blind luck. And the sun isn't done. Solar activity follows an approximately 11-year cycle, oscillating between quiet periods of solar minimum and violent periods of solar maximum, when sunspots, flares, and coronal mass ejections become far more frequent. The most recent solar maximum has brought intense activity, with the May 2024 solar storms producing auroras visible as far south as Puerto Rico, and registering as one of the strongest geomagnetic disturbances in over 2 decades. Carrington-class events are estimated to occur roughly once every 500 years on average, but smaller, still devastating events occur much more frequently. Storms half as intense as the Carrington event happen approximately every 50 years. In 1989, a far weaker geomagnetic storm knocked out power across the entire province of Quebec. In 2003, the Halloween solar storms produced some of the most powerful solar explosions ever recorded and forced satellite operators around the world to put their spacecraft into emergency standby mode. The sun is not misbehaving during these events. This is what it does. This is what it has always done. And here is something that makes all of this even more unsettling. The Carrington event may not have been the worst the sun can do. Not even close. Scientists studying tree rings and ice cores have found evidence of solar events that dwarf anything in recorded history. In the years 774 to 775 CE, a massive spike in carbon-14 was recorded in tree rings around the world. When researchers analyzed the data, they concluded that the solar event responsible was roughly 10 to 20 times more powerful than the Carrington event. There was no technological civilization to damage, so the only traces left are chemical signatures in ancient wood. An even larger event has been identified around 7,176 BCE, one that may have exceeded even the 774 event. These are not theoretical projections. These are measurements from physical samples. The sun has done this before, and the geological record makes it clear that it will do it again. The only question is when, and whether our civilization will be standing when it does. Some researchers have also looked at other stars similar to the sun, and found that they occasionally produce what are called superflares, eruptions hundreds or thousands of times more powerful than anything we have observed from our own star. For a long time, scientists assumed the sun was too stable and too slow spinning to produce such events. But more recent work has challenged that assumption. The question of whether the sun is capable of a true superflare remains open, and the honest answer is that we do not know. We have only been watching the sun with modern instruments for a few decades. The tree ring record suggests our star is capable of outbursts far beyond anything we have witnessed in the modern era. We are making assumptions about the sun's behavior based on an absurdly small sample of its lifespan, like judging the temperament of an ocean after watching it for 30 seconds. But even if we somehow manage to protect ourselves from solar storms, there is a much larger, much slower threat that no technology can prevent. The sun is dying, not quickly, not dramatically, but steadily, irreversibly, and in a way that will end all life on Earth long before the star itself runs out of fuel. Remember that 1% increase in luminosity every 110 million years? That process is accelerating. Within the next 1 billion years, the sun will become roughly 10% brighter than it is now. That does not sound like much, but it is enough to push Earth out of the habitable zone entirely. The increased solar energy will trigger a runaway greenhouse effect. The oceans will begin to evaporate. As water vapor, a potent greenhouse gas, floods the atmosphere, it will trap even more heat, causing more evaporation, in a feedback loop that cannot be reversed. Eventually, ultraviolet radiation from the brighter sun will split water molecules in the upper atmosphere into hydrogen and oxygen. The hydrogen, being light, will escape into space. Earth will be bled dry. The oceans will be gone, not reduced, not retreated. Gone. Earth will become a scorched, airless rock, remarkably similar to Venus. And then things get worse. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core. When that happens, the core will begin to collapse under its own gravity, heating up as it compresses, until hydrogen in a shell around the dead core ignites and begins fusing. This is the beginning of the red giant phase. The sun's outer layers will expand enormously. It will swell to roughly 256 times its current size, cool from white-hot to red-hot, and become thousands of times more luminous. Mercury will be consumed. Venus will be consumed, and Earth, sitting right on the edge of the expanding star's reach, will almost certainly be swallowed as well. Even if Earth's orbit drifts outward slightly due to the sun's decreasing mass, most models suggest that will not be enough. The planet will be dragged into the outer envelope of the dying star and vaporized. On Earth's surface, in the final stages before engulfment, iron will begin to melt. The crust and mantle will boil away. Everything that ever lived here, every fossil, every city, every trace of civilization, will be reduced to atoms inside the body of the star that once gave it life. After roughly 1 billion years as a red giant, the sun will shed its outer layers in a series of violent pulsations, creating a planetary nebula, a beautiful glowing shell of gas, expanding outward into space. And at the center of that shell will be what is left. A white dwarf, a collapsed remnant roughly the size of Earth, but containing most of the sun's original mass. It will glow faintly from residual heat, cooling over trillions of years, until it becomes a cold, dark cinder drifting through the galaxy, a black dwarf. The final state of our star. No light, no heat, no legacy. And yet, despite all of this, we have recently done something remarkable. In December 2024, NASA's Parker Solar Probe completed its closest approach to the Sun, flying just 6,100,000 kilometers above the surface, deeper into the corona than any human-made object has ever gone. It traveled at 690,000 kilometers per hour, roughly 191 kilometers per second, making it the fastest object ever built by humans. At that speed, you could fly from Washington, D.C. to Tokyo in under a minute. The probe's carbon composite heat shield endured temperatures approaching 1,000 degrees Celsius, while the instruments behind it sat at a comfortable room temperature. It flew through the very atmosphere that we do not fully understand, gathering data that may finally help us solve the coronal heating problem and better predict the solar storms that threaten our civilization. We sent a machine to touch a star, and it survived. Here's the truth about the sun. It is not a benign glowing orb that exists to warm your face on a spring morning. It is a thermonuclear furnace that has been running for 4.5 billion years and will run for billions more, growing hotter, growing brighter, growing more dangerous with every passing century. It has already come close to crippling our civilization, and it missed by nothing more than the timing of our orbit. It will eventually boil our oceans, strip our atmosphere, and swallow our planet whole. The sun gives life, and the sun will take it back. Every sunrise is a reminder of that bargain, whether we recognize it or not. The clock started ticking the moment the sun ignited, and it has never, not for a single second, stopped. If you want to keep exploring what the universe is really doing, subscribe. I'll see you in the next one.